Hey guys, in this quick video, that sounded weird then. I am going to be going through how we go from atoms to ions and why most elements actually want to be in an ion state rather than their usual atom state. So first things first is why we want to go to ions. So atoms, as we know, they have equal number of protons and electrons for each of the atoms, but that doesn't mean that, even though that's what we normally find, it doesn't mean that they're stable. For it to be a stable molecule, they need to have a full outer shell. So there's only one group of elements that are happily stable and never react to anything, and these are called the noble gases. And I've drawn a little bit of a periodic table here, just the first 3 rows. Obviously transition metals I've shortened down so it can fit in here. But the group that never reacts with anything is this one down the side, which is the noble gases, and made up of, for the first 4 is helium, neon, argon, and krypton. I don't know, possibly krypton. And I'm going to do a quick Bohr diagram on this side to show why. So helium its atomic number is 2. It's got 2 protons, 2 electrons. It has a weight of 4. 4 minus 2 equals 2 neutrons. So it's 2, 2, 2, 2, 2. Oh, it's down this side. P, 2, and 2. Alright, so then we've got our electrons left in the first shell. In the first shell, we can only ever have 2 electrons. Helium has 2 electrons. Sweet. Now, this means that it is currently completely stable. No matter what we do, unless we add a heave of energy to it, this is going to stay like this because it doesn't require anything to get to a full outer shell because it's already got there. Next one would be neon, which would have another ring around and 8 electrons. Alright, so what I'm going to draw now is the next element after. Ooh, that's a gross Rabiati thing. The next one is lithium. So lithium is the third element, so the next one along from helium. Third element, atomic number of 3, so 3 protons and not B electrons. 3, and if I have a bit of a squeeze, 6 point something, round that up, it's going to be 7. No, not 7. 4. It's almost like I don't know what I'm talking about. So again, P equals 3 and N 4. So now we've got 3 electrons. We draw our first shell, which can only ever have 2. Draw that in there. And then we draw 1 more, and we have that 1 left. Now, this outer shell here is not full. It is the closest it can be to not full. It's only got that singular electron. So, if it wants to get to the closest full shell, what can it do? It can either keep this shell and add 7 more electrons. So you can end up having this full. That's one possibility. Or what it could do instead is, if I find an eraser, there it is eventually it gets rid of that extra proton and it's just got those 2 electrons there. Ooh, there are 2 options. Now, to get rid of a proton and to gain a proton roughly requires the same amount of energy. And everything wants to use the least amount of energy. So is it going to be easier to gain 7 electrons or to lose 1 electron? It's going to be easier to lose an electron and get back to this one. So now we would, Li. Now electrons have a negative charge, right? So there's 3 protons and 3 electrons. Balanced out evenly, which means that the atom has a neutral charge. Now, if you take away one electron, it means you now have 3 positive charges and 2 negative charges, which means overall, the charge for lithium is now a positive 1 charge. Now, the thing is that once we've worked it out for lithium, because lithium is a nice easy one, we know something special about its column on the periodic table. We know that everything in the same column as lithium, when it turns into an ion, it's going to be +1. If you can hear some shouting in the background, that's just our good friend, probably in this class, still in this class, yes, Riley Apps out there playing handball and his mate with the long hair, shouting and screaming, so you can blame them if it's rather annoying. Now, we could go through and do this for each of these elements, but I'm not going to. I'm going to give you the quick hint. So this one has 1 extra electron in that shell, so it can either gain 6, yes, 6 plus 2 is 8, or it can lose 2. So if it loses 2, hey, guess what, guys, it's now lunchtime, yay! So if it loses 2, it's going to have a +2. Then we go on to the next one. This has 3 in its outer shell. Is it either going to lose those 3 or is it going to gain 5? It's easier to lose that 3. It's going to be +3. Now we get to carbon, or the row that carbon is in. This one's a weird one because it has 4 in its outer shell. So we can either gain 4 or lose 4. This is why carbon doesn't tend to react in a nice, easy way, I guess. Actually, just strike that off. Just cuts, never mind. But this one is a plus or minus if you ever do use it. Next one we go is nitrogen. Now nitrogen has 5 electrons in its outer shell. So it can either lose 5 electrons or it can gain 3 electrons. And it's always easier to do the one with the lower number. So if you've got a positive charge and a negative charge, and they're equal, there's no total charge. But if you add more negative electrons, what is the overall charge going to be? It's going to be more negative. And it's going to be more negative by a factor of 3 because you're adding 3 more electrons on, which means this is now -3. Then oxygen has 6 in its outer shell, so it needs to gain 2 electrons to be able to get a full outer shell and make it nice and stable. So by gaining 2, it's now got 2 more negative than it does positive, and as a result it has a -2 charge. And then the final one, fluorine, it has 7 in its outer shell. And is it easier to lose 7 or gain 1? Easier to gain 1. And if it's got 1 extra electron, it means it's got 1 extra negative charge, which means overall it's going to have a charge of -1. -1. And as we saw beforehand, helium has a full outer shell. It has no charge when it becomes stable because it's already stable in the form that it's in. So this is 0. So what this means is now that every single element that we're going to be looking at down this row has a +1 charge when becoming an ion. So lithium, sodium, and potassium always have a +1 charge. When it comes to the second column, beryllium, magnesium, and calcium always have a +2 charge. If we jump across past the transition metals, boron, aluminium, and Gavin, I don't know. We don't normally use these ones, but let's just call him Gavin, have a +3 charge. If we ever need to use carbon, silicon, or Jeffrey, that's spelled with a G, they have a +4 or -4 charge. Then if we ever need to use nitrogen, phosphorus, or arsenic, I don't know. Again, these ones you don't really need to know. We'll have a -3. If we ever use oxygen or sulfur or Se, it needs to be a -2. If it's ever fluoride, chlorine, or that's not beryllium, Br down there, it's going to be a -1. So you don't even have to do this whole thing here. You can just know, first row +1, second row +2. Transition metals, bit difficult, we'll let you know. Then, when we come back here, this row +3, plus or -4, -3, -2, -1, and the ones on the far side have no charge whatsoever. So, hopefully with this video it helped you understand why we have ions and why things just can't be in their atomic form. If you need to restart this video, please go and push the little red thing that's probably going to be here, all the way back over here. And if you're all good, I'll catch you in the next video. Yeah, that was a good one, I think.